So, good day everyone. Our topic for today is about processes, description, and control. The concept of process is fundamental to the structure of modern computer operating systems. So, its evolution in analyzing problems of synchronization, deadlock, and scheduling in operating system has been a major intellectual contribution of computer science. That is according to MIT Press 1980. So, at the end of the lesson, the students are expected to define the term process and explain the relationship between processes and process control blocks, explain the concept of process state and discuss the state transition the processes undergo, list and describe the purpose of the data structure and data structure elements used by an operating system to manage processes, assess the requirements for process control by the operating system, understand the issues involved in the execution of OS code, assess the key security issues that relate to operating system, and describe the process management scheme for Unix. So, all multi-programming operating system from single-user systems such as Windows for end users to mainframe systems such as IBM's mainframe operating system, ZOS, which can support thousands of users, are built around the concept of the process. So most requirement that the OS must meet can be expressed with reference to process. So the OS must interleave the execution of multiple processes to maximize processor utilization while providing reasonable response time. The OS must allocate resources to processes in conformance with a specific policy, while at the same time avoiding deadlock. The OS may be required to support inter-process communication and user creation of processes, both of which may aid in the structuring of applications. We begin with an examination of the way in which the OS represent and control processes. Then the latter part, process state, discusses process state, which characterize the behavior of processes. Then we look at the data structure that the OS uses to manage processes, and this include data structure to represent the state of each process and data structure that record other characteristics of processes that the OS needs to achieve its objective. Then next we look at the ways in which the OS uses this data structure to control process execution. And finally, we discuss process management in Unix, provides more example in the process management. So this lesson occasionally refers to virtual memory. Much of the time, we can ignore this concept in dealing with processes, but at a certain point in the discussion, virtual memory considerations are pertinent because virtual memory is previewed and discussed in the latter part, and a set of animations that illustrate concept in the chapter is available also. And okay, so what is the processes? So before defining the term process, it is useful to summarize some of the concept. So a computer platform consists of a collection of hardware resources such as the processor, main memory, I/O modules, timers, disk drives, and so on. Computer applications are developed to perform some tasks. Typically, they accept input from the outside world, perform some processing, and generate output. It is inefficient for application to be written directly for a given hardware platform. The principal reasons for this, of course, is the numerous applications can be developed for the same platform. Does it make sense to develop common routines for accessing the computer's resources? The processor itself provides only limited support for multi-programming, and software is needed to manage the sharing of the processor and other resources by multiple applications at the same time. And when multiple applications are active at the same time, it is necessary to protect the data, IOUs, and other resources use of each application from the others. The OS was developed to provide a convenient, feature-rich, secure, and consistent interface for applications to use. The OS is a layer of software between the applications and the computer hardware that support applications and utilities. We can think of the OS as providing a uniform, abstract representation of resources that can be requested and accessed by applications. Resources include main memory, network interfaces, file systems, and so on. Once the OS has created this resource abstraction for application to use, it must also manage their use. No, for example, an OS may permit resource sharing, and of course, and resource protection. Now that we have the concept of application system software resources, we are in position to discuss how the OS can and unorderly fashion manage the execution of applications so that resources are made available to multiple applications. The physical processor is switched among multiple applications so all will appear to be progressing. The processor and I/O devices can be used efficiently. So the approach taken by all modern operating system is to rely on a model in which the execution of an applications correspond to the existence of one or more processes. So several definitions of the term process include a program in execution, an instance of a program running on a computer, the entity that can be assigned to and executed on the processor, and a unit of activity characterized by the execution of a sequence of instruction, a current state, and an associated set of system resources. We can also think of process as an entity that consists of a number of elements. The two essential elements of a process are program code, of course, which may be shared with other processes that are executing the same program, and a set of data associated with that code. Let us suppose that the processor begins to execute this program code, and we refer to this executing entity as a process. At any given point in time, while the program is executing, this process can be uniquely characterized by a number of elements, include the following: identifier, state, priority, program counter, memory pointers, context data, I/O, status information, and accounting information. So the information in the preceding list is stored in a data structure as what we have here. We have figure 3.1, the simplified process control block. So that is created and managed by the operating system. The significant point about the process control block is that it contains sufficient information so that it is possible to interrupt a running process and later resume execution as if the interruption had not occurred. The process control block is the key tool that enables the OS to support multiple processes and to provide for multiprocessing. When a process is interrupted, the current values of the program counter in the processor's registers are saved in the appropriate fields of the corresponding process control block. In the state of the process is changed to some other value such as black or ready. The OS is now free to put some other process in the running state, and the program counter in the context data for this process are loaded into the processor register, and this process now begins to execute. Thus, we can say that a process consists of program code and associated data plus a process control block. So for a single processor computer, at any given time, at most one process is executing, and that process is in the running state. Now, For a program to be executed, a process or task is created for that program. So from the processor's point of view, it executes instruction from each repertoire in some sequence dictated by the changing values in the program counter register. Over time, the program counter may refer to code in different programs that are part of different processes. So from the point of view of an individual programs, its execute involves a sequence of instructions within that program. So we can characterize the behavior of an individual process by listing the sequence of instruction that execute for that process, such as listing is referred to as trace of the process. And we can characterize behavior of the processor by showing how the traces of the various processes are interleaved. So let us consider this very simple example. So in this figure, it shows a memory layout, no, of 3 processes. So we have the process A, B, and C. Which is, of course, presented by programs that are fully loaded in main memory. So in addition, there is a small dispatcher, no, program that switches the processor from one process to another. So this figure shows the traces of each of the process during the early part of their execution. The first 12 instructions executed in process A and C are shown. No? So from process B, execute 4 instruction, and we assume that the 4th instruction invokes an input-output operations for which the process must wait. So in this one, as what we have here, no, the first 12 instruction executed in process A and C, as what we have here, no, display the instructions executed in processes. Now, the same sequence of instruction is executed by the dispatcher in each instance because the same functionality of the dispatcher is being executed. We assume that the OS only allows a process to continue execution for a maximum of 6 instruction cycle, after which it is interrupted. So as you can see here, that is 1 to 6. So this prevents any single process from monopolizing processor time. So a two-state process model. The operating system principal responsibility is controlling the execution of processes, and this includes determining the interleaving pattern for execution and allocating resources to processes. The first step in designing an OS to control processes is to describe the behavior that we would like the processes to exhibit. We can construct the simplest possible model by observing that at any time a process either being executed by a processor or not. So in this model, a process may be in 1 or 2 states, running or not running. So when the OS creates a new process, it creates a process control block for the process and enter the process into the system in the not running state. The process exists is known to the OS and is waiting for an opportunity to execute. From time to time, the currently running process will be interrupted and the dispatcher portion of the OS will select some other processes to run. The former process move from the shaded areas indicated execution of dispatcher process first and for the running state to the not running state, and one of the other processes moves to the running state. So from this simple model, we can already begin to appreciate some of the design elements of the OS. And each process must be represented in some ways so that the OS can keep track of it. That is, there must be some information relating to each process, including current state and location in memory. And this is the process control block. Processes that are not running must be kept in some sort of key, waiting their turn to execute. So as what we have here in keying diagram, there is a single key. In each entry is a pointer to the process control block of particular process. So alternately, the key may consist of a linked list of data blocks in which each block represents on one process. We will explore this latter implementation subsequently. We can describe the behavior of the dispatcher in terms of this keying diagram. So a process that is interrupted is transferred to the key of waiting process. So alternatively, if the process have completed or aborted, it is discarded. In either case, the dispatcher takes another process from the key to execute. So the creation and termination of processes. Before refining our simple two-state model, it will be useful to discuss the creation and the termination of processes. Ultimately, and regardless of the model of process behavior that is used, the life of a process is bounded by its creation and termination. For the process creation, when a new process is to be added to those currently being managed, the OS builds the data structures that are used to manage the process and allocates address space in main memory to the process. So we describe this data structure in this figure, no? Four common events lead to the creation of process as indicated in this table 3.1. In a batch environment, such a process is created in response to the submission of a job. In an interactive environment, a process is created when a new user attempts to log on. In both cases, the OS is responsible for the creation of a new process. So an OS may also create a process on behalf of an application. So let's say, for example, if a request or if a user requests that a file be printed, the OS can create a process that will manage the printing. The requesting process can thus proceed independently of the time required to complete the printing task. Traditionally, the OS created all processes in a way that was transparent to the user or application program. And this is still commonly found with many contemporary operating systems. However, it can be useful to allow one process to cause the creation of another. For example, an application process may generate another process to receive data that the application is generating and to organize those data into a form suitable for later analysis. The new process runs in a parallel to the original process and is activated from time to time when new data are available. And this arrangement can be very useful in structuring the application. As another example, a server process, no example, the print server or the file server, may generate a new process for each request that it handles. So when the operating system creates process at the explicit request of another process, the action is referred to as a process spawning. No? Process and the spawn process is referred to as the child process. No? So when one process spawns another, the former is referred to as the parent process and the spawn process is referred to as the child process. Typically, the related processes need to communicate and cooperate with each other. Achieving this operation is difficult task for the programmer. So, process termination. This table actually summarizes typical reasons for process termination. So any computer system must provide a means for a process to indicate its completion. So a batch job should include a halt instruction or an explicit OS service call for termination. So in the former case, the halt instruction will generate an interrupt to alert the OS that a process has completed. So for an interactive application, the action for the user will indicate when the process is completed. Okay, so for example, in a time-sharing system, the process for a particular user is to be terminated when the user logs off or turn off his or her terminal. On a personal computer or workstation, a user may quit an application, and all of these actions ultimately result in a service request to the OS to terminate the requesting process. Additionally, a number of error and fault conditions can lead to the termination of a process. In this table, it lists some of the more commonly recognized conditions by conditions. So finally, in some operating system, a process may be terminated by the process that created it, or when a parent process is itself terminated. A 5-state model. So if all processes were always ready to execute, then the keying discipline suggested would be effective, as figure 3.5 a while ago. No? So the key is a first in, first out list, and the processor operates in round robin fashion on the available processes. However, even with the simple example that we have described, this implementation is inadequate. So some processes in the not running state are ready to execute, while others are blocked, waiting for an I/O operation to complete. Thus, using a single key, the dispatcher could not just select the process at the oldest end of the key. Rather, the dispatcher would have to scan the list looking for the process that is not blocked and that has been in the key the longest. A more natural way to handle this situation is to split the not running state into 2 states, the ready and block. So in this figure 3.6, we have added 2 additional states that will prove useful. So the 5-state in this new diagram is the running, the ready, block for waiting, new, and exit. And the new and exit states are useful construct for process management. The user attempts to log on to a time-sharing system or a new batch job is submitted for execution, and the OS can define a new process into stages. So number 1, the OS performs the necessary housekeeping course. An identifier is associated with the process. Any tables that will be needed to manage the process are allocated and built. At this point, the process is in the new state, and this means that the OS has performed the necessary actions to create the process but has not committed itself to the execution of the process. So, for example, the OS may limit the number of processes that may be in the system for reasons of performance or main memory limitations. So while a process is in the new state, information concerning the process that is needed by the OS is maintained in control tables in the main memory. However, the process itself is not in main memory. That is, the code of the program to be executed is not in main memory, and no space had been allocated for the data associated with the program. So while the process is in the new state, the program remains in secondary storage, typically this storage. So in figure 3.6 a while ago, as what we presented here, no? So this table na 3.6, no? It indicates the types of events and lead to each state transition of process. So the possible transition are as follows. So null to new, new ready, ready running, running exit, and running ready. Then, of course, running, then black, black, then ready exit, then black exit. So returning to our simple example, this figure shows the transition, each process among the states. So this 3.7. And this figure suggests the way in which a keying discipline might be implemented with two keys, no? A ready key and a black key, as each process is admitted to the system. It is placed in the ready key when it is the time for the OS to choose another process to run its select one from the ready key. So in the absence of any priority scheme, this can be a simple first in, first out key. So when a running process is removed from execution, it is either terminated or placed in the ready or black key. Of course, depending on the circumstances. And finally, when an event occurs, any process in the block key that has been waiting on that event only is moved to the ready key. And this latter arrangement means that when an event occurs, the OS must scan the entire block key, searching for those processes waiting on that event. So in the large OS, there could be hundreds or even thousands of processes in that key. Therefore, it would be more efficient to have a number of keys, no, and one for each event. So then when the event occurs, the entire list of processes in the appropriate key can be moved on the ready stage. So this one. Suspended processes. So the need for swapping. So the three principal stages just described is the ready, running, and block. Provide a systematic way of modeling the behavior of processes and guide the implementation of the OS. And some operating systems are constructed using just these three states. However, there is a good justification for adding other state to the model. To see the benefit of this new state, consider a system that does not employ virtual memory. So each process to be executed must be loaded fully in the main memory. So this time we have the process state, a transition diagram with suspense state. So we have the ready, the block, block suspend, and ready suspend. But before looking at the state transition diagram that encompasses the two new suspend state, one other point should be mentioned. So the discussion so far has assumed that the virtual memory is not in use and that a process is either all in main memory or all out of the main memory. So with a virtual memory scheme, it is possible to execute process that is only partially in main memory. If reference is made to a process address that is not in main memory, then the appropriate portion of the process can be brought in. The use of virtual memory would appear to eliminate the need for explicit swapping because any desired address in any desired process can be moved in or out of main memory by memory management hardware of the processes. So let us look now in this figure B. No, a while ago this will the suspend state. This time with two suspend state. So the state transition model that we have developed. So this will be the block suspend and the block suspend ready suspend. So this will be the block, then block suspend to ready suspend to ready, then ready to ready suspend. The new block ready suspend, and of course the exit state. Okay, so other uses of suspension. So far, we have equated the concept of a suspended process with that of a process that is not in main memory. So a process that is not in main memory is not immediately available for execution. So a process that is not in the main memory is not immediately available for execution whenever or whether or not it is awaiting an event. So we generalize the concept of suspended process. So when we say suspended process, there is a certain characteristics. The process is not immediately available for execution. The process may or may not be waiting on an event. The process was placed in suspended state by an agent, either itself a parent process or the OS, for the purpose of preventing its execution, or the process may not be removed from the state until the agent explicitly orders the removal. This table 3.3 no, lists some reasons for the suspension of a process. Okay, so we have the swapping, other OS reasons, interactive user requests, timing, and of course, finally, the parent process request. So in all of these cases, the activation of a suspended process is requested by the agent that initially requested the suspension. So the process description. The OS controls events within the computer system. So it schedules and dispatches processes for execution by the processor, allocates resources to processes, and respond to requests by user processes for basic services. Fundamentally, we can think of the OS as the entity that manages the uses of system resource by processes. And this concept illustrated here in our figure 3.10. In a multi-programming environment, there are a number of processes, P sub 1 to P sub n, that have been created and exist in a virtual memory. Each process during the course of its execution needs access to certain system resources, including the processor, I/O devices, and main memory. And in the figure, process P sub 1 is running at least part of the process in the main memory, and it has control of two input-output devices. Process P sub 2 is also in the main memory but is blocked wait for an I/O device allocated to P sub 1. Process P sub n has been swapped out and it is therefore suspended. So typical elements of process image, no? Operating system control structure. If the OS is to manage processes and resources, it must have information about the current status of each process and resource. The universal approach to providing this information is straightforward. The OS constructs and maintains table of information about each entity that it is managing. So a general idea of the scope of this effort is indicated in which shows 4 different types of tables maintained by the OS: memory, IO file, and process. Although the details will differ from one OS to another, fundamentally, one OS maintains information in these 4 categories. So we have the memory tables, the allocation of main memory to process, and the allocation of secondary memory to processes. So we have here the process attributes, no? With identifiers, process identification, and process state informations. So we have here the different data structuring, inter-process communication, process privileges, memory management, resource ownership, and utilizations. So with respect to the process identification, in virtually all operating systems, each process is assigned a unique numeric identifier, no? So otherwise, we were mapped that allow OS to allocate the appropriate tables based on the process identifier. So the third, we have also the process identification. So in virtually all operating system, each process is assigned a unique numeric identifier, as I mentioned. The process state information consists of contents of processor registers. While a process is running, of course, the information is in the register. So when a process is interrupted, all of this register information must be saved so that it can restored when the process resumes execution. The nature and number of registers involved depend on the design of the processor. Typically, the register set will include user visible registers, control, and the status register and stack pointers. The third major category of information in the process control block can be called, for want of a better name, the process control informations. So this is the additional information needed by the OS to control and coordinate the various active process. So this will be the Pentium EAF flags register bits. So this one is the and an operating mode bits. Of course, we have the control bits and the operating mode bits. Then the condition codes covered the AF, CF, OF, PF, SF, and ZF flag. So here is the user processes and virtual memory. So of course, in this figure, suggest the structure process image in virtual memory. So each process image consists of a process control block, a user stack, the private address space of the process, and any other address space that the process share with other processes. So in this figure, each process image appears as a contiguous range of addresses. So in actual implementation, this may not be the case. It will depend on the memory management scheme and the way in which control structure are organized by the operating system. So The process control block may contain structuring information, including pointers that allow the linking of process control blocks. Thus, the keys or the cues that were described in the preceding section could be implemented as linked lists of process control blocks. So for example, the keying structure of figure 3.8a could be implemented as suggested in figure 3.14. So the role of the process control block. The process control block is the most important data structure in an OS. Its process control block contains all of the information about the process that is needed by the OS. So the block are read and or modified by virtually every module in the OS, including those involved with scheduling, resource allocation, interrupt processing, and performance monitoring and analysis. One can say that the set of process control blocks defines the state of the OS. And this brings up an important design issue because a number of routines beyond the OS will need access of the information process control block. The provision of a direct access to this table is not difficult. Each process is equipped with a unique ID, and this can be used as an index into a table pointers of the process control block. So this will be the process creation. Assign a unique process identifier to the new process. Allocate space for the process. Initialize the process control block. Set the appropriate linkages and create or expand other data structure. So for the process switching, when to switch processes, clock interrupt, IO interrupt, and memory fault. So table 3.8, mechanism for interrupting execution of a process include the interrupt, trap, and supervisor call. So with a trap, the OS determines if the error or exception condition is fatal. No? If so, then the current running process is moved to the exit state and a process switch occurs. So if not, then the action of the OS will depend on the nature of the error and the design of the OS. It may attempt some recovery procedures and simply notify the user. So it may do a process switch or resume the currently running process. And finally, the OS may be activated by the supervisor call from the program being executed. So for example, a user process is running and an instruction is executed that requests an IO operation, so such as a file open. So this call results in a transfer to a routine that is part of the operating system codes. Now the use of the system call may place the user process in the black state. So the inclusion of an interrupt stage as part of the instruction cycle is the mode switching. It recalled that in the interrupt stage, the processor checked to see if any interrupts are pending, indicated by the presence of an interrupt signal. So if no interrupts are pending, the processor proceeds to the fetch stage and fetches the next instruction of the current program in the current process. So if an interrupt is pending, the processor sets the program counter to the starting address of an interrupt handler program and switches from user mode to kernel mode so that the interrupt process code may include privileges. So execution of the operating system. The OS function in the same way as ordinary computer software in the sense that OS is set of programs executed by the processor. So the OS frequently relinquishes control and depends on the processor to restore control to the OS. So if the OS is just a collection of programs and if it is executed by the processor, just like any other program, is the OS a process? If so, how it is complicated? In this figure, interesting questions have inspired a number of design approaches. So it illustrates in this figure range approaches that are found in various contemporary operating systems. And we have the non-process kernel. So in any cases, the key point here is that the concept of process is considered to apply only to users' program. So the operating system code is executed as separate entity that operates in privilege mode. So the execution with user process. So an alternative that is common with operating system on smaller computers is to execute virtually all OS software in the context for a user process. The view is that the OS is primarily a collection of routines that the user calls to perform various functions executed within the environment of the user's process. So the process-based operating system. Another alternative illustrated, of course, is to implement the OS as collection of system processes. So as in the other option, the software that is part of the kernel execute in a kernel mode. So in this case, however, major kernel functions are organized in separate processes. Again, there may be a small amount of processes switching code that is executed outside any process. So the security issues. So the security issues. An OS associates a set of privileges with each process, and these privileges dictate what resources the process may access, including regions of memory, files, privileged system instruction, and so on. Typically, a process that executes on behalf of a user has the privilege that the OS recognizes for that user. A system or utility process may have privileges assigned at configuration time. On a typical system, the highest level of privilege is referred to as an administrator, supervisor, or root access. Root access provides access to all the functions and services of the OS. So with root access, a process has complete control of the system and can add or change programs and files, monitor other processes, and receive network traffic and alter privileges. A key security issue in the design of any OS is to prevent or least detect attempts by a user or a piece of malicious software or malware from gaining unauthorized privileges on the system, and in particular from gaining root access. So we have the system access threats. So system access threat falls into two general categories: intruders and malicious software. Intruders. One of the most common threats to security is that intruder or the other viruses, often referred to as the hacker or cracker. In an important early study of intrusion, it identified three classes of intruders: the masquerader, misfessor, and clandestine users. The masquerader is likely to be an outsider. The misfessor generally is an insider, and the clandestine user can be either an outside or an insider. Intruders attack range from the benign to the serious. At the benign end of that scale, there are many people who simply wish to explore internet and see what is out there. At the serious end are individuals who are attempting to read privileged data, perform authorized modification to data, or disrupt the system. The objective of the intruder is to gain access to a system or to increase the range of privileges accessible on a system. And most initial attacks use system or software vulnerabilities that allow a user to execute code that opens a backdoor into the system. Intruders can get access to a system by exploiting attacks such as buffer overflows on a program that runs with certain privileges. Alternatively, the intruder attempts to acquire information that should have been protected. In some cases, this information is in the form of a user password. With knowledge of some other user's password, an intruder can log into a system and exercise all the privileges accorded to the legitimate users. So, on the other hand, malicious software, perhaps the most sophisticated types of threats to computer system, are presented by programs that exploit vulnerabilities in computing system. Such threats as referred to malicious software or malware. In this context, we are concerned with threats to application programs as well as utility programs, such as editors and compilers and kernel-level programs. Malicious software can be divided into two categories: those that need a host program and those that are independent. The former, referred to as a parasitic, are essential fragments of programs that cannot exist independently of some actual application program, utility, or system program. Viruses, logic bombs, and backdoors are example. So the latter are self-contained programs that can be scheduled and run by the operating system. Worm and boot programs are example. So we can also differentiate between those software threats that do not replicate and those that do. The former are programs or fragments of programs that are activated by a trigger. So example are logic bombs, backdoors, and boot programs. So the latter consists of either a program fragment or an independent program that, when executed, may produce one or more copies of itself to be activated later on the same system or some other system. Viruses and worms are example. Malicious software can be relatively harmless or may perform one or more a number of harmful actions, including destroying files and data in main memory, bypassing controls to gain privileges access, and providing a means for intruders to bypass access code. So how about the countermeasure? Intrusion detection is a security service that monitors and analyzes system events for the purpose of finding and providing real-time or near real-time warning of attempts to access system resources in an authorized manner. So IDS, or intrusion detection system, can be classified as follows. No, so this one: host-based IDS, network-based, sensors, analyzer, user interface. So authentication. In most computer security contexts, user authentication is the fundamental building blocks and the primary line of defense. So user authentication is the basis for most types of access control and for the user accountability. So we have the process of verifying identify claim by or for a system entity, and that's identification step and verification step. We have also 4 general means of authenticating a user identity, which can be used alone or in combinations. So we have something the individual knows, something the individual possesses, something the individual is, static biometrics, or something the individual does, dynamic biometrics. Actually, all of these methods properly implemented in use can provide secure user authentication. However, each method has problems. No, an adversary may be able to guess or steal a password. Similarly, an adversary may be able to purge or steal a token. So a user may forget a password or lose a token. Further, there is an insignificant administrative overhead for managing password and token information on systems and securing such information on system. So with respect to biometrics authenticators, there are a variety of problems, including dealing with false positives and false negative, user acceptance, cost, and convenient. The access control implements a security policy that specifies who or what no, may have access to each specific system, resource, and the other type of access that is permitted in each instance. So an access control mechanism mediates between a user and system resources such as applications, operating systems, firewalls, router, files, and databases. The system must first authenticate a user seeking access. Typically, the authentication functions determine whether the user is permitted to access the system at all. Then the access control functions determine if the specific requested access by this user is permitted. A security administrator maintains an authorization database that specifies what type of access to which resources is allowed for this user. And the access control functions consults this database to determine whether to grant access. An auditing functions monitors and keeps a record of user access to system resources. And of course, the firewall, no? Firewalls can be an effective means of protecting a local system or network of system from network-based security threats, while at the same time affording access to the outside world via wide area networks and the internet. Traditionally, a firewall is a dedicated computer that interfaces with computers outside a network and has special security precautions built into it in order to protect sensitive files on computer within the network. So it is used to service outside network, especially internet, connection and dial-in lines. Because personal firewalls that are implemented in the hardware or software and associated with a single workstation or PC are also common. So design goals for firewall, of course, all traffic from inside or out, inside to outside and vice versa must pass through the firewall. And this is achieved by physically blocking all access to the local network except via the firewall. And various configurations are possible as explained, of course, in some other discussion. Only authorized traffic as defined by the local security policy will allow to pass, and various types of firewalls are used, which implement various types of security policies. The firewall itself is immune to penetration, and this implies the use of hardened system with a secured operating system. Trusted computer systems are suitable for hosting a firewall and open required government applications. So this will be the unique process state. Again, Unix system V or 5 makes use a simple but powerful process facility that is highly visible to the user. So system processes run in kernel mode and execute operating system code to perform administrative and housekeeping functions such as allocation of memory and process swapping. User processes operate in user mode to execute user program and utilities, and in kernel mode to execute instructions that belong to the kernel. A user process enters kernel mode by issuing a system call when an exemption is generated or when an interrupt occurs. So a total of 9 process states are recognized by the Unix SVR4 operating system. And these are listed here in our figure 3.9 as state transition diagram for this figure 3.17. So this figure is similar to with the 2 Unix sleeping state correspond to the 2 block state, and which the Unix employs to running state to indicate whether the process is executing in a user model or mode or kernel mode. So distinction is made between the 2 states, the ready to run and memory, and preempted. So preemption can only occur when a process is about to move from kernel mode to user mode. So while a process is running in kernel mode, it may not be preempted. Okay, so this makes Unix unsuitable for real-time processing. So the Unix processing, we have the user level, register context, and system level context. And for the table entry, so we have the process status, pointer, size, user identifiers, and others. Excuse me. How about the Unix U area? So this will be the Unix U area. So it indicates entry that correspond to the U area. So actually, the process control, the process creation in Unix is made by means of kernel system call. So we have the process issued for fork request that the OS operating system following the functions. So all of this work is accomplished in kernel mode in the parent process. When the kernel has completed these functions, no, it can do one or the following as part of the dispatcher routine. So stay in parent process, transfer control to child process, and to transfer control to another process. It is perhaps difficult to visualize this method of process creation because both parent and child are executing the same passage of code. So the difference is this, no? When the return from the fork occurs, the return parameter is tested. If the value is 0, then this is the child process, and the branch can be executed to the appropriate user program to continue execution. If the value is non-zero, then this is the parent process, and the main line of execution can continue. So again, the most fundamental concept in modern OS is the process. So the principal functions of the OS is to create, manage, and terminate processes. So while processes are active, the OS must see that each is allocated time for execution by the processor, coordinate their activities, manage conflicting demands, and allocate system resources to processes. So to perform its process management functions, the OS maintains a description of each process or process image, which includes the address space within which the process executes and a process control block. The latter contains all of the information that is required by the OS to manage the process, including its current state, resources allocated to it, priority, and other relevant data. So during its lifetime, a process moves among a number of states. The most important of these are ready, running, and blocked. No? A ready process is one that is not currently executing, but that is ready to be executed as soon as the OS dispatches it. The running process is that the process that is currently being executed by the processor. In a multiple processor system, more than one process can be in this state, and a block process is waiting for the completion of some events such as the input-output operations. Again, a running process is interrupted either by an interrupt, which is an event that occurs outside the process and that is recognized by the processor, or by executing a supervisor call to the OS. So in either case, the processor performs a mode switch, transferring control to an operating system routine, and the operating system, after it has completed necessary work, may resume the interrupted process or switch to some other process. And that's it for today. Thank you for listening. Godspeed, everyone.